Hello, this is Mrs. Nearing, and we're going to be doing a video of calorimetry practice set number 2. We're going to be looking at finding the delta H of some reactions. So this first reaction we're looking at, it's an acid-base reaction, so it's hydrochloric acid reacting with sodium chloride. And you will notice that the reaction written below here is the net ionic equation, because this right here is the molecular equation. But the HCl, the NaOH, and the NaCl, they're aqueous. They're all going to ionize. The water is the only thing that's not going to ionize. So what's left over is this reaction right here. All right. So we've got a temperature change, and we're asked to find energy. So whenever this is the case, we want to say, hey, that looks like a calorimetry problem. So we're going to use this equation right here. The temperature change is the final temperature minus the initial temperature. So it looks like the final temperature is 29.9 degrees. The initial temperature is 23 degrees. And with thermo, it is important to think about sign. So it is good to think about which order you subtract these. And it's also important to think about sig figs, because when we subtract these, we will see that the temperature change is 6.9. Notice the temperatures had 3 sig figs in it, but the temperature change only has 2 sig figs. Okay. The specific heat is, did they give us the specific heat? No, I think earlier at the beginning of the practice set it says to assume the specific heat for all of these is the same as that of water. So I think that said that at the top of the page. And then the mass. Here is what trips people up often, is using the wrong mass. So make sure you are using the mass of whatever you're taking the temperature of. And if you imagine this scenario right here, we have a thermometer sitting in your calorimeter, and what that is sitting in here is a combination of 100 mils of HCl and 100 mils of NaOH. So they mix together, they formed a homogeneous solution. So in this scenario, you want to add together the two masses. Okay, and I think at the top of the page it told us to assume the density is 1 gram per milliliter. And if not, then it should have said to do that. So we can assume that if you have 100 milliliters of solution, that's going to be 1 gram per milliliter. So that is going to be 100 gram solution. And you've got 2 of those, so the mass is going to be 200 grams. And I'm writing it this way with that, 200 with the decimal right here. That at the end makes these zeros significant. So this number would actually have 3 sig figs as written. Or another way, if I wanted to write 100 with 3 sig figs, is I could write it like this. So if my density is to 3 sig figs, then my final mass should just be to 3 sig figs. So that's why I wrote it out that way. So when we plug in to solve for Q, that's going to be 200 grams. My specific heat is also probably to 3 sig figs. My temperature is just to 2 sig figs, so that's going to be limiting the sig figs in this problem here. So 200 times 4.18 times 6.9 is going to be, if I plug this in my calculator, I get 5,768.4 joules. But if I want to round that to 2 sig figs, that's 5,800 joules. Okay, and again, that's more accurately representing how confident we are in our answer there. So if you think about what's going on, that is, when we're doing calorimetry, this is the amount of energy absorbed by the surroundings. So we can never measure the actual reaction itself. All we can do is see the impact the reaction has on its surroundings. So the temperature of the surroundings increased, meaning our reaction released energy. So I'm actually going to skip down to C right now. This shows us our reaction is exothermic. And the reason why we know this is because we are measuring the surroundings, and we saw the surroundings increased in temperature, which means and we were able to calculate that they gained 5,800 joules of energy. And if I skip up here, if the surroundings gained 5,800 joules of energy, that means the reaction released that much energy. So that's where we have this kind of equation right here that we saw in the notes, where it says Q reaction is negative Q of the calorimeter. So getting at the idea that the Q of the system that we are trying to observe is going to be equal in magnitude but opposite of sign of what the change in the surroundings. So that means that our reaction, if the surroundings gained 5,800 joules of energy, that means our reaction gave off that much energy. So our reaction lost that much energy. And I'm going to convert that into kilojoules by dividing it by 1,000. And now I want to put it into kilojoules per mole. So whenever we divide by moles, the rule of thumb is to use the limiting reactant as your source of, how many moles got used up. So if we look up in this scenario, it looks like we have two solutions. And when we have solutions, we find moles by using the molarity. So remember, molarity is moles per liter. So to find moles, I would take my molarity times my volume. So my molarity is 0.76 and my volume is 0.10 liters. So that means I have 0.076 moles of H+. And then if I look at my NaOH, you'll see the numbers are exactly the same. So I've got equal amounts of H and OH. And it looks like they react in a 1-to-1 ratio. So who's my limiting reactant? Well, they kind of both are, right? It looks like I don't have an excess reactant. They're both going to get equally used up. So if they're both the limiting reactant, then you just pick one of them because it doesn't really matter. So I'm just going to divide my kilojoules by the number of moles that react, which is 0.076 moles. So notice how I don't add these two things up. I'm just going to use one of them. Okay. So 5.8 divided by 0.076, and I end up getting negative 76 kilojoules per mole. That's to 2 sig figs. You may have gotten a slightly different answer if you had left the original unrounded number in your calculator. Maybe you got like negative 75 or negative 77 or something like that. With rounding, that's fine too. But in the end, it should be negative. It should have 2 sig figs. That's what it should look like. Let's do one more that's similar here. Another reaction here. We are reacting aqueous barium nitrate. Remember, all nitrate compounds are soluble with some sodium sulfate. All alkali metal compounds are soluble. This looks like a double displacement reaction. So the sodium and the nitrate's going to come together. That's doubly soluble. And then the barium and the sulfate are going to come together. That is not on my list of things that are soluble, so I'm going to assume it's insoluble. I'm going to balance it right here with a 2. And then I'm going to ionize my aqueous things. Whoops, I left a 2 off there. So my aqueous ionic compounds, they are going to split apart into ions. So over here, and it is important to understand what is going on here with these complete ionic equations, because you might need to recognize what this would look like in a solution. And then I'm going to notice my spectator ions are sodium and nitrate. So they're there in the solution, but they're just not part of the reaction. So with the net ionic equation, we will leave them out, and we will just show the things that are actually involved in the change that's occurring. So the barium ion and the sulfate ion combine to make barium sulfate. And then I'm going to find the amount of heat gained or lost using the calorimeter. So I see the word calorimeter, and hey, I know I'm going to use this equation. If you don't see the word calorimeter, you can look for the fact that they're giving you a temperature change. That's another kind of giveaway there. This is a situation where we're mixing together two aqueous solutions, so we're going to add together the masses. So again, I'm assuming that our density is 1 gram per mil like we did on that earlier problem. So it's going to be 200 grams is our total solution mass. The specific heat we are assuming is the same as that of water, so 4.18 joules per gram degree Celsius. And this could be given to you, that'll be given to you in a problem. It could be given to you in a variety of sig figs. They might say 4.2, it might say 4.184, so just see what the problem's giving you. And then the temperature change, the final temperature is 29.7. The initial temperature is 25.0. I think it's helpful to write down somewhere what this actually is so you can think about sig figs. So 29.7 minus 25.0, if I'm doing this in my head right, is 4.7 degrees. So notice there's only 2 sig figs in this problem. So if we put this together, it's 4.7 times 4.18 times 200. You end up getting, 3,929.2 joules. But I want to round that to 2 sig figs, so that's 3,900 joules. And remember, we are measuring the surroundings, so this is the amount of energy gained by the surroundings. So if I'm trying to figure out what happened in the reaction, is the opposite. So if the surroundings gained 3,900 joules of energy, that is because the reaction released that much energy. And then I'm going to convert that into kilojoules here. And then I want to make this a ratio, kilojoules per mole. So remember, with moles, we want to use the limiting reactant. That's a good rule of thumb here. And so let's look at what we are given. These things are both solutions. So we find moles by using the volume and molarity. And it looks like our volume is 100 mils and the molarity is 1.5. And that's the same for both reactants. So molarity is moles per liter. So I can rearrange that, and moles is molarity times liters. So our molarity is 1.50. Okay. Our liters is 0.10 liters. And so that looks like we have 0.150 moles of barium. And we have the exact same numbers for sulfates. And this is how I often see them present this on the AP test. A lot of times one of them, like, you won't necessarily have a limiting or an excess. They might be given in equal molar amounts. Or they might make it very obvious that one's in limiting. Like, they'll say that by saying, all of the barium gets used up. That's a good clue that, like, oh, that means that's the limiting reactant. Okay, so since they're both limiting, I could use either the moles of barium or sulfates. Doesn't matter. So what we're going to do to find delta H is you take negative 3.9 kilojoules divided by 0.150 moles, and 3.9, and again, depending on whether you rounded or whether you kept this number in your calculator, you might get a different result. But I got negative 26 kilojoules per mole as my answer. And this reaction is exothermic, and we saw that what we're looking for here is the surroundings had an increase in temperature. So that means the reaction lost energy while the surroundings gained energy. All right, thanks for watching. Hope this was helpful.